So here we are for the final sloppy talk of today by Pierre Montalbano on conflict-free learning in mixed integer linear programming and weighted constraint satisfaction problems.
Yes.
Please.
Yes, thank you very much. So yes, my name is Pierre, and I'm going to present you one of the work I did during my PhD with Simon de Givry and Georges Castrivolo. So initially, my PhD was on weighted constraint satisfaction problem, so WCSP, and we were a bit jealous of PBO and SAT because they have a nice learning mechanism, and we don't have that. So we wanted our own learning mechanism, and so we designed this conflict-free learning. And while we were designing this, we observed that it can be used inside a MILP solver. So as I think most of you are more at ease with MILP than WCSP, I'm going to present you this conflict-free learning approach from the point of view of the MILP solver. So I think this work is kind of fun because it is a crossover between Pseudo-Boolean optimization technique, constraint programming techniques, and MILP techniques. So let's go. Let me go with conflict-free learning in MILP. So let me go straight to the point. Our objective today will be to learn the lower bounds of the subproblems we visit during the search. So suppose we are doing a branch on branch search. We have each node of this search tree that corresponds to a subproblem, and this subproblem we are going to solve it to optimality by visiting the subtree. And it should be nice to save the information that we already solved that subproblem, and so to learn a constraint and say, okay, I know the optimal solutions of this subproblem, it was this, and I add a new constraint to save this information. So to be more precise, let's go with a small example. And so here is a 0-1 integer programming. So you have, okay, an objective function, only 6 variables here. Important. Yes, okay, great. Okay, and so you have two constraints. I added the constraint xi must be inferior or equal to 1 because we are going to solve the LP versions of this this MILP, and this is why we need this xi must be inferior or equal to 1 constraints. So first things we are going to do is that we are going to write this problem into its standard form. So in the standard form, we only have equality constraints. And this means that we have to add slack variables. So you can see the S here, which is a slack variables. And for the constraint xi must be inferior or equal to 1, I add this slack variable that I name xi bar, which basically corresponds to not xi. Okay, so we have xi plus not xi must be equal to 1. And those slack variables are real variables. So why do we use this standard form? You will understand in a few slides. Okay, so another thing that we do that is uncommon maybe for MILP is to restrict the domain of a variable. So to remove the variables, we are going to increase its coefficient by a large value. For example, to remove x1 here, we are going to modify the objective function and say, okay, the coefficient of x1 is 100. So this 100 is chosen to be sufficiently large, like a very large upper bound, such that in any optimal solution, we are never going to use these x1 variables to 1. So why we do that? We do that because if we only modify the objective functions, then the set of primal constraints and dual variables at every node of the search tree remains exactly the same. So for today, it will be kind of hidden inside this the slide, but behind this, the theory, we need these information here to prove what I'm going to show you today. Of course, here I said the set of primal constraints remains the same. Of course, we are going to learn some constraints, so it's not completely true, but you get it while we only modify this objective function, and we don't want to add extra constraints like, okay, x1 must be equal to 0. Okay, so let's go. Let's solve this small problem using a branch on bound. So here, small branch on bound algorithm. So the bounds are only computed by solving the LP of the problem. Okay, so that's classic. So let's look at this blue node here. You can see that this blue node, it corresponds to a subproblem. When we arrive at it, we solve the LP, we find, okay, the lower bound is 14. Then we can see visit the two child nodes here, and we can see, okay, the best solution that I found is not 14, it is 15. So here I could have done better. So here maybe I can add a new constraint And this constraint, it will tell me if I solve again this blue node, the sub-problem is from the blue node, the LP versions, then I can say my lower bound is 15, okay? Because it is an information that I obtain by doing zero. And I can do that for every node of the search tree. So at the green node, I can look at the two child nodes and obtain, okay, I can learn a constraint that says the optimal solution is 17. Similarly, for the red node in, I can look at the two child nodes and say, the best I could do was 15 and not 12. So why would it be interesting? So it means that if I meet again the second time the blue node, I will directly have that the optimal solution is 50. I will directly have the lower bound is 15. So it is better than 14. But here we still have one thing that is not very cool. It is that in this 14, basically you can see that there are kind of 12 that is coming from upper decision, that is coming from the red node here. And so if we learn the constraints that the blue node, we have an optimal solution of 15, then it entirely depends on what happens before the node and what happens after. Okay, so this is not interesting because the decision we make to arrive to the blue node, we are not going to then make them a second time during the search because it's a simple function. So what will be more interesting for us, it looks only at the increase of lower bound. So here, same function bound, but I highlight here only the increase of lower bound. So here in the blue node, we increase the lower bound by 2, here by 1, and so on. And here we could learn a constraint that say, okay, when I arrive at the blue node, I can increase my lower bound by 3. And this time it's different because here it is an increase of lower bound by 3 independently of what happened before. It only used information by getting lower in the search. And it means that this subproblem, we can meet it several times during the search. For example, we can think of the dynamic programming used to solve the knapsack problem. We know that we are going to solve small subproblem, and then we are going to use that information to solve larger subproblem, and so on. And so the solutions for one subproblem, we are going to use it several times during the dynamic approach. So this is where it can be useful. Okay, so to kind of sum up, each node corresponds to a subproblem. During research, we often solve to optimality these subproblems. We don't want to save this information to not have to compute it again during the search. And to do that, we are going to use a conflict-free approach. So conflict-free, it's in opposition with the conflict-based learning, where here you can learn a constraint without triggering conflict to learn this constraint. So you can basically learn it at any time during the search, at any node of the search tree. Okay, why is it interesting? So it is interesting because in the case of the WCSP solving, the main way to solve this problem is to compute lower bounds and not to remove a variable. So it's not like in PBO where the main propagation is to remove the variables one by one until you reach a conflict. Here, you are going to increase the lower bound until you reach a conflict. So it's a different way to solve the problem. So that's why we are more interested in the lower bounds and not exactly how we remove the variable. So this conflict-free learning, it has already been used. It has already been used in MILP by Witzig Jacob. So it uses Farkas constraints, which is a linear combination of primal constraints guided by an LP dual solution. So those Farkas constraints, often they are used to prove the infeasibility of a problem, but you can also use it on any feasible solutions, on any feasible problem by using a dual feasible solution. And if we do that, we cannot say that this Farkas constraint explains a lower bound. So what does it mean? It means that on the right-hand side of the constraint, you will find exactly the lower bound. So if you find that the lower bound of the problem is 12, then the right-hand side of the Farkas constraint will be 12. And on the left part, it will kind of indicate which combinations of constraints and objective functions coefficients has led to this increase of lower bound. Okay? But the Farkas constraints, they are linear combinations of primal constraints. And thus, if you add it to your LP solver, it will not help him to get better bounds because it is just a linear combination of primal constraints. That's why we see here, he said, okay, we can go deeper in the search tree, find new information, and then come back to tighten those Farkas constraints. And if you do that, he shows that you can prune more values during the end of the search. But as you can see, it's still only good to prune more values. It's not good to increase the lower bound. And us, what we want to do, we want to have a constraint that if I add this constraint, I can guarantee you that the lower bound will be this amount. And so first things we need to do is to characterize such constraint. So this constraint, we call them memo constraint. So memo constraint, what is it? It's a constraint where all the coefficients in the constraint are lower than the coefficients in the objective function. And if this property is true, then you know that the relaxed optimal solution of the problem is at least the right-hand side of this memo constraint. Okay, so I will just show you one example just after. And we are lucky because there exists a family of Farkas constraints that are exactly memo constraints that are verifying this property. So there are the Farkas constraint issued from a dual feasible solution. So let's go back to example. Here we have also small MILP. Okay, on the right side here, I written the optimal dual solution. So on the first line, you can see the dual solutions of the variables corresponding to the first constraint and so on. So we are going to multiply each constraint by this dual solution and sum everything. And we obtain this Farkas constraint here. So this Farkas constraint, what you can see is that every coefficient in this constraint is lower than the coefficient inside this objective function. So you have 3x1, 3x1, 4x2, 3x2. You have 0, not x5, and here you have -1, not x5, and so on. And on the right-hand side, you have 12 corresponding to the optimal relaxed solutions of the problem. And here it's quite clear, at least I hope, that here you have basically small coefficients must be equal to 12. So it is kind of obvious that the big coefficient must be greater or equal to 12. Okay, so that's why it is a memo constraint and it justifies the lower bound of here 12. Okay, great. We have a Farkas constraint, there are memo constraints, so we can add this constraint to the problem to guarantee that I will increase my lower bound. But here, we said that we are looking only at the increase of lower bound and not at the brute lower bound. If I use the Farkas constraint like this in my function bar, it will justify always the brute lower bound, but not only the increase. So how can we capture only the increase? We can do that by using strategy coming from the WCSP community, which is basically rewriting the objective function. So from these LP optimal solutions, we can rewrite the objective functions to find an equivalent problem. And basically what we do is that we are using the reduced cost. And what happens here, what is nice, is that we are using these optimal solutions first to compute the Farkas constraints, and we say that it kind of saves the subset of cost justifying the increase of lower bound. And at the same time, we use the same optimal solutions to rewrite the objective functions and those kind of to erase from the objective functions the information that we use inside the Farkas constraint. Okay, so what does it look like? It looks like this. We have a problem P here. We generated a Farkas constraint here, okay? And on the right-hand side, you have the new problem P prime with the new objective function. Okay, so here, the objective function corresponds to the reduced cost of all the variables. So for those who don't know what are the reduced costs, another way to see it is, okay, here I began a problem P, I have 3x1. In my Farkas constraint, I said, oh, I need 3x1 to justify my lower bound of 12. And thus it only remains 0x1 in the new objective function. Similarly, I begin with 4x2. I need 3x2 here. So it remains only x2 in the new objective function. And similarly for not x5, I begin with 0 not x5. I need -1 not x5. And thus it remains a positive amount of not x5 here. And what you can observe as well is that the right-hand side of the constraint here, it is 12, so the LP optimal solutions. And you can see that this 12 is now appearing as a constant in my new objective functions. And this is why now we are only highlighting the increase of lower bound, is that if we now continue the search and find a new Farkas constraint, this Farkas constraint, it will only use those costs, and it will not touch to the 12. Okay, or the 12 will appear as a constant, and so we can simply remove it. This means that the new Farkas constraint, it only uses that, and so it will only use it will only justify the increase of lower bound. Another thing you can notice is here, you can see that the slack variables are appearing in the new objective function. And this is exactly why we needed our MILP to be written in standard form. Because without the standard form, we don't have the slack variable, and we cannot do this reformulation of the problem. Okay?
So sorry, I'm trying to understand this. This seems to be an important slide.
Yes.
Yes. Okay. So the problem P prime.
Yes.
When I'm looking at this, so you have your original problem. You relax it. You run your LP solver. You get basically the dual multipliers or whatever you get the multipliers from the optimal solution to the dual.
That's
fine. And that gives you that by definition gives you a constraint where the left-hand side is like at most the objective, but could be less.
Yes.
And now basically what you're saying here, that for P prime, you're saying that we know that the lower bound is 12, and this is even without caring about what you did to x2. Like if you screw up x2, then the lower bound will be even worse. But
yes.
sort of regardless of what you did to x2, I promised you that 12 is a lower bound.
Yes.
Kind of. On the other hand, how should we understand this x5 and x6? That's sort of actually, what are we saying there? We're saying that, yeah, you can. So basically all of these terms that you have left is like, okay, 12, you'll never go below that. That's hopeless. But the things that are remaining, well, it could get even worse if you screw up. And let me tell you ways in which you could screw up.
Yes, for example, here.
Is that a way to sort of think about it?
Yes, maybe the two S here, the slack variables corresponding to the first constraint is maybe easier to explain. Basically, if I want, so the LP solver, most of the time it will tightly solve this constraint. So we have 10 equal 10, basically, and S most of the time would be low. And basically what it says there, it's there if you go beyond 10 and that you must use this S variable, then you will screw up even more, and so you will have to pay something. Okay, so basically I think that's what means this those slack variables and why does they appear in this new objective function.
And you're saying that the coefficients that I see here in P prime are the reduced cost?
Yes, they are exactly the reduced cost.
Exactly the reduced cost. Thank you. Thanks a lot.
Okay. So, okay, we are up here. We have forecast constraints, there are memo constraints. Thanks to rewriting the objective function, we can even highlight only the increase of lower bound. But still, there are still forecast constraints, so linear combinations of the primal constraints. So they are not going to help the LP solver. How can we do better? We can use Pseudo-Boolean Optimization technique and more precisely resolution technique. So here we are going to develop a rule from the fusion resolution rule that already exists, that Jacob presented yesterday. So on one side you have not x1 plus something. On the other side you have x1 plus the exact same thing. And basically you can simply remove away x1 and not x1 and deduce this new constraint where you don't have x1 or not x1. And on the right-hand side you have the minimum of the two right-hand side. Okay, we do a slightly more general rule, which is the memo resolution rule. So basically, you can have two constraints, any constraint with any coefficient, and you can still remove away these xg variables from the two constraints. But if you do that, then you have to take the maximum coefficients of all the variables outside g on the left-hand side, and on the right-hand side, you have to take the minimum of the two right-hand side. So you have to kind of take the maximum on the left and the minimum on the right. So it seems very aggressive because you cannot do much worse, I mean.
But WJ and WJ prime, you want them to match probably?
No, we don't care about the value of WJ and WJ.
Oh, right, okay.
It can be anything, we don't really care.
Oh, right.
And just we can say, okay, we don't need them anymore. We can simply
that's actually a good point. Yes.
But if we do that, we have to take this maximum here and the minimum of the right-hand side, which is does not seem very good. But why this rule is interesting, and why is it called memo resolutions? It's simply because if you have two memo constraints here, then the resulting will still be a memo constraint. Why? Because you can see here, the coefficients, they do not increase. So it means that they cannot be greater than the objective functions if they were already lower in this situation. So it means that if you take two memo constraints to obtain a new memo constraint. And even better, suppose that here you have almost a memo constraint, meaning that the only variable that is breaking the memo property, so let's suppose it is x of g, so it means that wg is greater than the coefficient in the objective function of g, but all the other variables are fine, then this memo resolution is going to remove these coefficients, and thus at the end we can obtain a memo constraint. Okay, so from two non-memo constraints because of this variable x of g and not xj, we can obtain a new memo constraint. And we are going to use that property, and you are going to see that the variable x of g here, we can kind of choose whatever we want, but in our strategy, it will be kind of obvious which x of g we are going to use. Okay, so now we have all the pieces we need to define the general idea of the search, of the procedure. So suppose we are in this situation, we are looking at node A, B, and C. So what we are going to do is that we are computing the Farkas constraints at node A, and you are transforming the objective functions to obtain a new objective function f prime. Okay. Then we are going to visit the two child nodes. So, and we compute for both of them a memo constraint, so CB and CC for the two nodes B and C. Second step is applying memo resolutions on CB and CC. Okay. Then we sum the resulting constraint with CA, and here the magic appears because these constraints are the sum of the result of the memo resolution plus CA. It is a memo constraint at node A. So that seems pretty convenient. So this constraint is a memo constraint. We can learn it and then return it to the parent node to continue the recursive procedure and continue learning memo constraint.
And how do you do the memo constraints for B and C? By running this? Or no, wait.
Yes, exactly. So
what's the base case?
So the base case is if B or C is a leaf. So in this case, if it is a leaf, you just have to compute the Farkas constraint and return it. If it is not a leaf, then you compute the memo constraint by computing the Farkas constraint plus the memo resolutions of the two child nodes, of the memo constraint of 10 child nodes. Okay, so the base case is my node is a leaf and I compute only the Farkas constraint. Okay, so maybe let's look at the example to see clearly what is happening here. So we are at this node here, the well node. So the MILP look like this. So you remember that to remove a value, we simply increase its coefficient. So that's why you have 100x2 and 100x3. Not x3, it's a decision variable that we mentioned. You can see them. We have x2 is equal to 0 and x3 is equal to 1. So not x3 must be equal to 0. We have our modified objective functions, okay? So we solve the AP, we find that the optimal solution is 2. We compute a Farkas constraint, so the right-hand side is 2 because it corresponds to the increase of our bound. We rewrite the objective function, so we modify those coefficients. You can see that now the lower bound is 14, so 12 plus 2, okay? That's nice. Another thing interesting to see is that here the branching decision variable what says x1 must be equal x of 3, so it must be equal to 1, so not x of 3 is equal to 0. And you can see that its coefficient here is 100, and here it is 3, and it is kind of something that is always true. Basically, if you increase your lower bound, you will always find the branching variable to appear inside the Farkas constraints. And moreover, it will be kind of the only variable that is breaking the memo property, let's say, meaning that if I remove the 100 x3 here and I put 0, then this variable here is breaking the memo property. And this is something that is always true, that the only variable that is going to break the memo property is always the branching decision variable. And why? It is because we increased in its objective function the coefficient, so it is a very high coefficient. So if we remove that decision, then that's why we do not have this memo property. Okay, so we continue. We compute memo constraint at node CB and CC. So I give you the constraint it's here. So here it's simply the forecast constraint because B and C are leaves. Okay, so you can see that on the right-hand side, you do have the 4 corresponding to the +4 and the 1 here corresponding to +1. So you apply memo resolution. As I said here, the branching variable is x6. So you can see that in this constraint, you have not x6 appearing. And in this constraint there, you have x6 appearing. So you can always resolve with that variable. So we are always going to resolve away the branching decision variable. So here, x6, we apply our rule. We obtain this constraint. So we observe that this constraint is a greater or equal constraint. So we need to add the slack variable once again. So we add a new variable, S1, to make it an equality constraint. And what is nice is that this constraint here is a memo constraint at node A prime. So the node A after the reformulation. So it corresponds to this problem here. Okay. So this constraint CBC is a memo constraint of this problem. Then what we do is that we sum this constraint with CA. So the forecast constraint at node A. And here we obtain this new constraint here. And no, it is kind of magic, but this CABC is a memo constraint at node A. And you can see that the right-hand side is indeed 3. So it's corresponding to the +2 coming from here and the +1 coming from here. Meaning that if we manage to get again to this subproblem A, we will directly find that the optimal solution will be increased by 3, and we don't have to do the rest of the search. So to be more precise here, suppose that, so here we did our strategy or learning mechanism for this part. Suppose we do it also for here, and that we learn here this constraint. Okay. Suppose that knows that we are going to the other, to the left branch. Okay, where x1 is equal to 0. We obtain this problem here. And basically, without the learned constraint, without this constraint, the optimal solution is 13. But if you add this learned constraint, the optimal solution is directly 16, and you can directly end the search. Okay, so why is it working on this example? It is working here because you can see that x1 and x2, they kind of have the same behavior, meaning that if I assign x1 to 1, I have to select x2 to 0, and this third constraint basically with 3x3 plus this must be equal to 8 because we assign x1 to 1. And similarly, if I assign x2 to 1, then x1 must be equal to 0. And this constraint reads again 3x3 plus must be equal to 0. So that's why we obtain 2 times the kind of almost the exact same problem. And that's why this constraint here is useful. Okay, so we did little implementations to see, okay, is it working? So we did a little Python script using a Cplex API. So we did a very basic branch and bound solver. So we do depth first search branch and bound. We branch on the first fractional variable that we found. We still apply value removal by bound propagation. So it corresponds to the propagation that is done in the Pseudo-Boolean Optimization. And at each node of the search tree, we solve the LP. So this is the basic versions, the versions that we call no learning. And then we add all learning mechanisms that we call the memo bound, for which at each node of the search tree, we are going to rewrite the objective function. We are going to apply node consistency. So node consistency is simply that you take your objective function, you look at all the variables, and you look at, okay, if I do the lower bound plus the coefficient of one variable, does it give something greater than the upper bound? If it is true, then clearly I can remove this variable because if I select it to 1, then I will obtain something greater than my upper bound. Okay, so it's a very simple, very simple way to remove some variable. And we also learn memo constraints. So we test it on small instances. So first on knapsack problem. So we have between 100 and 300 variables, random weights and profits. So why did we choose that? We chose that because, say in the beginning, we know that dynamic programming is very efficient on this, and that basically it's solving some problem and using this information to solve larger subproblem and so on. So we wanted to see, okay, can we do the same with memo bound? Is it able to learn the optimal solutions of the subproblems? Okay. So here we are only looking at the number of nodes because the small Python script we did is clearly node optimized, and my knowledge of simplex API at this time was quite limited. So I know that it wasn't the most efficient way to implement what we did. So that's why we are only looking at the number of nodes and to see the scaling on the number of nodes to see if, okay, is the learning mechanism learning something useful. So the most interesting color here are the blue and the green one. So in blue, you can see the versions without learning. So basically, between 100 and 300 variables inside the knapsack, you increase your number of nodes by 7, or multiply by 7. While in green, with our learning mechanism, first we can see that for each for each instances, so there is like 20 instances for each size, so it is the average. So for each instances, we can see that we have a lower number of nodes, so apparently it's learning something useful. And moreover, you can see that the scaling is much less important. It's something like multiplied by 3.15 or something like that. So apparently, we are able to learn something useful in this case. And another situation, we still have a variant of the knapsack problem, here with a conflict graph, meaning that we have still Boolean variables, we still have only one knapsack constraint, but on top of that, we had a conflict graph. So if two variables are conflicting, we cannot select them both in this solution. Okay, so we have between 0.1 and 0.3 density of the conflicting graph. Okay, so we have different type of instances. Here, the R stands for random. So it means that the weight and the profit of all the variables is completely random. In the C case, it means that the weight is completely random, but the profit is always correlated to the weight. So those instances are harder than completely random. Then in superscript, you have a multiplier for the capacity. So the higher the capacity and the harder are the constraints, are the problems. Then you have the number of variables inside the knapsack. And then you have the density of the graph. So once again here, the interesting part is between no learning and memo bound. The other are just for yes, comparison, but the comparison is not very fair. So that's why we are more interested in this part. So we can see again that memo bound apparently is learning something useful because it has less nodes than no learning. Another thing that we can notice is that the difference between no learning and memo bound decreases as we increase the size of the conflict graph. So how can we interpret that? Basically, as we increase the size of the conflict graph, we are getting further away from a pure knapsack problem. And as we are getting further away from the knapsack problem, the conflicting graph is kind of parasiting our ability to learn the knapsack constraint, basically. So that's why we observe that. But still, it means that even if we don't have a pure knapsack problem, it is still apparently able to learn something useful, even if it is not in the obvious cases. Okay. And once again, it's because without telling memo bound that it is a knapsack problem, it's completely able to detect it by itself that it is a problem where it can learn something useful. Yes, we will come back. Let's first time.
We didn't. You didn't start in time, so.
Yes, well, but I have some slides also for WCSP. So, so here is what I present to you. It's kind of the beginning of the research. We only have a proof of concept to validate our theory, but of course we need to implement it in a fully functional solver. How does it combine with other existing algorithms? How does it combine, for example, with conflict-based learning? How can we do that? Also, I didn't say a word about that, but for example, when I say we apply value removal and stuff like that, we need somehow to inform all learning mechanisms that we remove some variables. Meaning that for each time we remove a variable, we need to create a kind of an explanation of why we remove that variable and then plug it inside our learning mechanism. So this means that if you want this to work inside a fully functional solver, there are plenty of things that we need to take care and say, oh, in this situation, we have to do that. In this situation, we have to do that, and stuff like that. Also, all the heuristics, we know that the efficiency of the learning mechanisms depends on them. For example, can we do restart? How can we select the constraint we want to learn? Should we keep all of them? Should we remove some of them? Can we strengthen the constraints by applying other resolution mode or other strategy? And so those questions are very important, and for the moment we don't have any insight on what would be very nice. And so it could be cool to show some theoretical results. For example, how is it comparable to dynamic programming? We saw that apparently it does something with an abstract problem. Can we verify this theoretically, saying something like we are not going to explore more nodes than the size of the dynamic table, for example, or something like that? It would be nice to have such proof. We don't have yet such proof, but I hope that sooner or later we will have. So before I continue, do you have any question on this work? Did you understand what I did, or was it maybe a bit too difficult?
Maybe a quick high-level recap. So you somehow, how can we view this? You solve the LP relaxations and generate lower bounds at all the leaves.
Yes.
And then you're somehow going to use this memo resolution to sort of propagate these bounds higher up in the tree.
Exactly. So maybe if I come back.
And then you had an example of this, how this somehow helped you get a lower bound that you wouldn't have seen otherwise.
So if I come back here, for example, what happens here is, so here I prove that the increase of lower bound is 1, here it is 4. So I do a memo resolution, and it will give me a constraint where the right-hand side is 1. So corresponding to the minimum to that. And the left-hand side, it's kind of the cost that justifies that the increase of lower bound is 1. Then I send up this constraint. I sum up with the constraint I obtained here, so with the information that I can increase my lower bound by 2. And so it gives me another constraint where the right-hand side is +2, +1. So it's a +3, so corresponding to this size. And on the left side, I still have the cost that was used to justify this lower bound of 3. And then again, I send this cost here, and I do the same thing here. I say, okay, between +5 and +infinity, what is the lower bound? It is +5. I send it here. Here I have +0, so I have nothing to do. And so I just to get again that constraint where it is +5 on the right-hand side, and I send it here. And here again, I apply memo resolution between this constraint with +3 and this constraint that I obtain here with +5. And I obtain here a new constraint with the right-hand side +3. And if I learn this constraint, it will help me when I'm getting to the right-hand side of the constraint of the tree. And so in the end, if we do that for the whole search, basically, at the root node, we will get a constraint where the right-hand side is exactly the optimal solutions of my problem. And on the left side, I will basically get the subset of costs inside my objective functions that justify this lower bound. Okay, and so we can do that because of these 3 pieces, which is rewriting the objective functions, generating Parcas constraints using the dual solutions, and then using memo resolutions to get those constraints together and combine them. Okay, so we have the 3 pieces that we are using here. Okay, I hope it was a bit more clear. Okay, so now let me present just how it is connected to WCSP. Okay, so first of all, what are WCSP? So most of the time, we introduce them by presenting graphical models. So graphical models are a type of graph where the nodes represent discrete domain variables. So here, for example, the boxes. The nodes corresponds here to also the value of each variable, so ABC here. And the edges, or hyper edges, corresponds to interactions between variables. For example, here you only have binary interactions between two variables. Okay? Depending on what you mean by interactions, you can define different things. For example, the Bayesian networks works with probabilities, and us, in our case, we are going to be interested in cost. So the interactions will be cost, and it gives us the cost function networks. So here is the definitions of the cost function. So a cost function, it takes a scope, A, and so a set of variables, and it associates a cost, so a non-negative integer, to each tuple in the scope. Okay, so for example, here you have a unary cost function, so a cost function with only one variable, x, for example, here, and you can see that for every value, we assign a cost. For example, here, if I assign x to A, it will cost me 2. Here I have a binary cost function, so between two variables. And you can see that similarly, we list all the possible tuples inside the scope, and we associate to it the cost. The cost of plus infinite, it corresponds to a completely forbidden tuple. I cannot select that inside my solution. And thus, we can represent hard binary constraints. So hard constraints, just like in the constraint satisfaction problem, it's simply with a case where you only have infinite cost, meaning that you cannot select this tuple, and zero cost, meaning that if you select this, it's nice, it costs you nothing.
And A and B, we can think of them as true and false. So these are just values in our domains.
Yes.
For some reason, we call A and B.
Yes, it's because in general, we are not looking only at binary variable. And most of the time, the domains of the variable is pretty large. At least it's where the WCSP is often the best. It's where the domains of the variable is pretty large. It can be, yes, up to 36 or things.
But they're typically like categorical, so they're not like integers, so that one value is larger than another, but they're just, values,
yes.
A, B, C, whatever.
Yes,
no relation.
Exactly, yes.
Okay. Mm-hmm.
Okay, so when we have a list of cost functions, so we have a list of discrete domain variables, we have a list of scopes, and for each scope, we define a cost functions. This is what we call a cost function networks. And trying to find the complete assignment that's minimizing the sum of all the cost functions, it is what we call the weighted constraint satisfaction problem. So this problem is NP-hard to solve, and it appears in many different situations. So there is a frequency assignment problem. In our laboratory, we are very interested by the protein design problem, and so on. So it can be convenient in some situations. Okay, so small example. So here is a small WCSP. So you can see we only have two variables. So we have three cost functions, two unary and one binary cost functions. Our objective is to minimize the sum of all of this. So do you know what is the best solutions here, for example? Can you figure it out? It's so difficult.
A probably, X is B and Y is A.
Yeah, we are going to set, yes, X equal B, Y is A, and it does cost 2. Okay, 2 coming from X equal B, it costs 2. Y equal A costs 0, and we can see that X equal B, A, it costs 0. So in practice, how can we solve those problems? We are going to do a branch and bound, and we are going to use software consistency algorithms to get the bounds. Okay, and for that, we are going to use equivalence preserving transformations. That corresponds, to the rewriting of the objective function that I told you before. So an equivalence preserving transformation is simply the transfer of cost from one cost function to another. And we do this transfer such that the two problems are completely equivalent. So for example, here, we are going to transfer a cost from the binary cost functions here to the unary cost functions here. So we are going to take a cost from all the tuples that uses X equal A, and we are going to take that cost and put it on the unary cost functions where X equal A. So it looks like that. So you can see we decrease all the tuples that use X equal A by 2. And to keep the equivalence, we have to increase the cost of the tuples that use X equal A here. So we obtain this new problem, which is completely equivalent to the previous one. And now you can notice that, okay, I observe that whatever I chose for X, it will cost me 2. So what I do is that we're going to transfer this cost to a very particular cost functions, which is f empty set. So it's the cost functions with a completely empty scope. And this cost function will appear as the natural lower bound of my problem, as it is a constant. So here, I have this new problem here, and I don't need to be very smart here to say that, okay, my lower bound is probably 2 here, because it appears as a constant here. And so that's what the soft consistency algorithms are going to do. They are going to move around the cost, and they're going to try to maximize this f empty set. So they're going to maximize the lower bound at each node of the substrate. Okay, so yes, at each node of the substrate, I produce a sequence of cost to transfer to increase my f0. The problem is that the optimal sequence to do that, we can put it as a MILP. It is what we call the local polytope. But solving this LP is very expensive. And sometimes we cannot do it in a very decent time. Like just solving the LP can take more than 1 hour or 2 hours. So solving this problem to optimality is completely impossible. So that's why we are looking only at sub-optimal solutions. And in particular, that's what the local consistency are doing. So just like in the CSPs, they only are looking at a local level. So for example, one cost functions and the unary cost functions that are linked to it, for example. And they are going to prune the locally inconsistent values and define a sequence of PPTs. So I won't enter into the detail. You have plenty of level of arc consistency, getting better, stronger bounds or not. But most of the time, the better is the lower bound, and the more expensive this consistency level is to enforce. Okay, one other strength of weighted constraint problem is that you can define R the global constraints inside, or even soft global constraints. And but you need to define the dedicated propagator for this field. Okay, so now what is the relationship with this conflict-free learning? It's simply that in CFM, so we know an LP, which is the local polytope. We know that the soft consistency algorithms are going to get us dual feasible solutions of this local polytope. And we also know that they are natively reformulating the problem, so they are natively rewriting the objective functions. So basically, we need to do nothing to get it implemented because we just use to sub-consistency algorithm, and this part is done. And here we just have to kind of transfer to kind of look at what operation has been done inside the WCSP to get a dual solution and then do the algorithm. Okay, so here I said it's very simple, but if I don't have a result to show you that we implemented it inside the WCSP solver, it is because it's not that simple for many reasons. First reason is here we don't have the slack variables, for example, inside it, because we use only a discrete domain variable. So the slack variable is not, because it's not possible or it's very hard to represent it inside this solver. So that's why there are still some questions to answer before having the concrete implementations of these things inside the WCSP solver. And that concludes my thoughts. Thank you for listening. Do you have any question?
No, questions for Pierre?
On slide 44, you showed this minimization of, one further, 45, I guess. The minimization function is not linear because there's a second degree term, just fxy, right?
It's linear because we can see basically here you just have 4 things. You have basically x equal a, y equal a must be equal to 3. So you can represent it as a Boolean variables taking value 1 if x equal a and y equal a. So two things. So if you want to represent it into an ILP solver or MILP, you are going to find the linear functions. But in reality, these functions, we never represent it explicitly inside the solver. It's kind of an obvious operation.
Okay.
So here I present it like this for the problem, but inside the solver, it is only trying to increase this lower bound, this f0. And so it's not really trying to minimize some kind of objective functions. And if you want to do it inside a MILP, then you can do it somewhere to find the linear function.
But
Okay.
so a cost function is like a cost function. It has a scope of a number of variables, and then for every combination of assignments to these variables, you will have like basically you have a table with for every possible assignment, what is the cost of that particular assignment.
Yes.
And then the problem is linear in the sense that the total cost of a cost function network, like given a total assignment, you just sum up the cost of all the cost functions.
Yeah.
And what would as you said, like I guess what you said that you could sort of define indicator variables for all the rows and then sort of write it as like fxy row 1 is true precisely if x equals a in
yes
y equals a, and then you would actually, I guess, get a 0, 1 ILP. But if you send that to one thing, the arity of the cost functions, that could be arbitrary, or here is only binary?
Yes, most of the time, most of the time there are two kinds of constraints. There are the small arity constraints, like 2 or 3, where we can afford to represent all the possible tuples, because of course it is costly in memory to represent all the possible tuples, especially if you have a large domain variable. So we have this kind of constraints, and then there are kind of the global constraints, which can be any arity constraints. So global constraints like all different linear constraints or stuff like that. And for this, we need a dedicated representation, because explicitly we're writing the cost of every tuple. So we take an exponential size in memory. And that's part of a reason why using an ILP solver to solve this kind of problem is not efficient. It's because you have to explicitly have a 0, 1 variable for every possible tuple. And if you increase the size of domain size of x and y, it will become very large.
And is it possible to say, like how, okay, so you say when you have a problem that is somehow natural to write in this form, then ILP solvers will not be so good. These are kind of, but this is also seems similar to constraint programming also, I guess, because you could have global constraints. You say anything about like when WCSP solvers would be good, when would, a standard like CP solver, like, I don't know, or tools or something, like how would they compare, do you know?
I have to, I think it's, yes, when the good cases in situations are when there are a lot of binary constraints with possibly large domains, discrete variables. And in these situations, the algorithms that are used for this kind of setting is very efficient. So that's the case, for example, for the protein design problem, where WCSP solvers are very efficient and CP solvers it's more complicated. And most of some contests, the differentiation is that, okay, it's working only on optimization problem here. So we are looking at lower bound and upper bound, while some CP solvers are very dedicated to decision problem and only finding the solution.
And do you see, and because this solution method that you mentioned of somehow transferring costs, and then apparently there is this LP. I don't know how the fact that there is an LP which describes exactly how you should transfer costs. Is this hard to see? I mean, how long? Like, suppose you were, to explain this, would we need like 5 minutes or 1 hour or a day?
Let's see.
Because a priori it's not obvious at all to me. So I'm just wondering if this is something, if I just squint at it in the right way, I'll see it, or is like, no, this is a deep thing you need.
We have to write the corresponding LP, and especially we have to look at the dual of this LP. So it's kind of a complex visualization, because the LP is already tough to write, and the dual version is also tough to write. So I think without this information, it's hard to see the connection between moving cost around and the LP. It really lies inside the dual optimal solutions, and I think it's difficult to see that without having it on paper in front of it. So I can give you the reference if you want.
Okay. So it sounds a bit complicated. things.
Yeah.
The conclusion. So, and is there any scope for this other things we've been talking about? I don't know, implicit hitting set, core guided search, these kind of things. Does it at all, like, would there be a way to somehow say, do like, I don't know, core guided WCSP or implicit hitting set CSP, or just?
It was an idea that we had with George, but it stayed at the point of, oh, okay, it would be nice to look at these directions and to see if it is possible. So definitely it could be interesting to look in that direction, but I don't think it is very trivial. Like, it's not straightforward, like just apply this and it's
I
working.
think there is a paper that does I
Ah, okay.
implicit sets I've seen. Probably.
Okay, then some already exists.
Was there maybe a CP 2024 presentation somehow related to this, some workshop?
Actually, the paper is slightly.
So any other questions? Let's then thank Pierre again.
Thank you.